Well, now we know how to compare means of two populations based on their samples, and closely related problem, how to estimate effects when you change a factor from one level to another, and then you would like to see what kind of effect it produces, for example, if we talk about response variable, yield of reaction, and any other things. Okay. So we know that in this case, we estimate effect. It's simply a difference of mean outcomes. Mean, we have two samples. One sample, it's all outcomes of our experiment we obtained using one level of our factor. So in our example, it was 120 and 240 seconds, right? So the time that we run the microwave oven to make a popcorn. And then we simply compute the average value for the percent of popped corns for each of these levels separately. And the difference between this average is the observed effect. So the expected effect we also define as a difference of the population average that we can estimate using, for example, confidence intervals and so on. But what to do if you have three different levels of your factor? For example, you still have one factor. So in this case, it's a brand, the popcorn brand, for example. And then you have three different popcorn brands. And you would like to find out which one is best, or if there is at least any difference among these three brands that you use. So apparently in this case, we cannot define the effect as we defined before, because we cannot compute difference of three values. I mean, mathematically we can, of course, but it will have no physical meaning, because difference by default, it's a distance between two values. So when you compute difference of three values, it's not the same, it doesn't have the same meaning. So we need to find out how to solve this problem. So we need to find out how to define effect, first of all, when you have three or more different samples coming from three or more different populations, and also how to solve this, how to find this effect, how to estimate it, how to make an inference, and so on. Well, like in the previous case, we have actually a similar problem, right? We have three populations. If you talk about percent of popped corns, then its population will be if all outcomes, all these percentage values we get if we run this infinite amount of times, right? And then we assume that in this particular case that populations are normally distributed. And then the outcomes of our experiment we consider as a sample, as a random sample that comes from these populations, right? So again, we have the assumption or maybe requirement that the variance, the standard deviations of these populations are the same, because we don't change the random factors, right? We change only one systematic factor, so it's kind of a reasonable assumption. And then we can describe any value taken from any population as follows, right? So the value comes from population with expected value mu a, and this is the random part. This is the variation, the variability of these values within one population, right? So this is very similar to what we had in this two-sample t-test, but in this case we have three populations and three samples, and therefore our null hypothesis still is no effect, so it means that the populations have the same means. Okay, so there is no difference in populations. But how to define an effect and how to actually make a test for the effect? Well, if you want to use, for example, two-sample t-test in this case, and if we want to test this hypothesis, we can actually split it into three smaller tests. So we can make a pairwise testing. So we compare A and B first, then we compare A and C first, and then we compare B and C. Okay. So because we have three possible pairwise combinations, if we have three different populations, so we can run three tests instead of one. But it means that we have a kind of several null hypotheses, right? So this one is our global or main, maybe principal null hypothesis, global. And these three hypotheses, right, they are local hypotheses. And remember, we test the global hypothesis. So this is our aim. Our aim is to find out how likely our sample came from population where this null hypothesis is true. But to do that, I suggest you to run several small tests with local hypothesis. And that's kind of a solution, right? But this solution has a little problem. If null hypothesis is true, you can accept it only if all these local tests also accept the local null hypothesis. But you reject null hypothesis if any of these tests fails. So it means that if, for example, this is accepted, and this is rejected, you will reject null hypothesis. If this is accepted, rejected, you will reject null hypothesis. So you have many possibilities to reject null hypothesis, right? And only one possibility to accept it. But what kind of problem it can pose? Let me show you a very simple example. Let's say we indeed make a test for 3 different populations. Like in this case, we can estimate effect from 3 different brands of popcorns. And let's say that we work with significance level of 0.05. In this case, if null hypothesis is true, the global null hypothesis is true, we have for every single test, we have a chance to accept it as 0.95, right? So we will accept null hypothesis in 95% of the cases because you remember the significance level, it's a chance to make type 1 error. It's a chance to reject null hypothesis, although the null hypothesis is true. So we have this chance in every of these tests. And therefore, if we reject null hypothesis in 5% of the cases, we will accept it in 95% of the cases, right? So this is the chance that we accept the second hypothesis, and this is the chance that we accept the local hypothesis, right? But when we accept the global one, only if all local hypotheses are accepted. What's the chance that we will accept this one and this one and this one if this is a probability for each local hypothesis to be accepted? Well, if you recall block number 1, where we discussed the probabilities, you know that if we have several events, the probabilities that all these events happens is a multiplication, it's a product of the every local event probability. So it means that the probability to accept the global null hypothesis, this one, is 0.95 times 0.95 times 0.95. And that's the chance that we will accept it, if although the null hypothesis is true. What's the chance to make type 1 error? It's 1 minus this, and it gives you, so you will reject null hypothesis in 40.33% of the cases, not 5% as we expected to have. It's almost 3 times larger. And that's what is called multiple comparison problem. Actually, multiple comparison problem arises not only in when you use t-test to test this big hypothesis, the hypothesis where you have more than 2 populations, but also every time you need to run several tests, for checking a single null hypothesis, you have this multiple comparison problem. Because you remember, you accept null hypothesis only if all local tests are accepted. Okay. The more tests you run to check this null hypothesis, the more higher chance will be that you will make type 1 error. So we'll reject it although the null hypothesis is correct. So in our terms, it means that you will claim that you see an effect, also the effect is just random. It's not present, in fact. Right. And actually, I must say that this is a big issue. Even kind of big scientists actually have this, forget about this problem, the multiple comparison problem. You can Google for Seralini affair. Seralini is a scientist. As far as I remember, he was kind of a biologist who have a lot of science about influence of GMO, genetic modified products on, for example, health of people and animals. And there was a big scandal where people found out that actually he published results which are not statistically justified. He had a lot of issues with statistical calculations and actually not accounting for multiple comparison problem with one of them. You can also find another paper, it's called Published GMO Studies Find No Evidence of Harm when corrected for multiple comparison. And that's a very nice paper which it gives you an overview of several of such studies where people simply forget that multiple comparison problem exists. So I highly recommend you to read at least the about Seralini affair and this paper, so you will be aware better about the multiple comparison problem. But now let's talk about how to solve it. Well, the idea is following. The simplest solution you have, it's to reduce the alpha inside the local tests. So if you want to get the final probability to reject the correct null hypothesis of 5%, it's the initial alpha that we have, right? It means that you need to reduce this probability in every single test, in every local test. So let me show you an example. In this case, I divided to 3. Why 3? You probably understand, because I have 3 tests. And let's see, it's kind of approximation as well. It's a simplification, but in most of the time it will work. Let's check it, right? So this is my new threshold. I should compare a p-value inside local tests. So let's see. So in this case, this is the chance, this is what I compare p-value with. And if null hypothesis is true, that's the chance that I will reject it incorrectly, right? But on the other hand, it means that this is the chance that I will accept this particular null hypothesis. Again, for the second test, this is the chance that I will reject it. If null hypothesis is true, this is the chance that I will accept it. And the same for the third test. Now, the chance that I will accept all three hypotheses, and therefore I will accept the global null hypothesis, it's a multiplication, it's a product of these three probabilities. And if you calculate them, you will find out that it's almost 0.95. So therefore, if you compute the chance to make type 1 error, it will be 0.05, exactly what we aim at. This little workaround, it's called Bonferroni correction. Bonferroni, it's a name. So the idea is simple. If you require n tests for checking a one single global null hypothesis, and if you accept this global null hypothesis, if all tests are accepted, then simply reduce the significance level for every local test as alpha divided to n, where alpha is your original significance level for the big global null hypothesis, and n is the number of tests. Again, it's a simplified version of this Bonferroni correction, but most of the time it will work. So let me just show you another example where, for example, I use alpha 0.01. So for the global hypothesis, alpha is 0.01, so it means that I would like to have 1% chance to make a wrong decision, to make type 1 error. So it means reject global null hypothesis, also it's correct, right? What it means? It means that if I need to run 3 local tests, if I want to use t-test to check this null hypothesis, my alpha inside this local test should be 0.0033. That's exactly 0.01 divided to 3, right? So let's check. So in this case, I have this probability to reject it if null hypothesis is true, right? And this is probability to accept it. In this case, it's the same. In this case, it's the same. And now what's the chance that I will accept all 3 null hypotheses? It's a product of these 3 probabilities, right? And if you calculate it, you will get 0.99, which means that the chance to make type 1 error will be almost exactly 0.01, the one that we actually wanted to see. Okay. So if indeed you need to run several local tests, doing pairwise comparison or in any other things, maybe you should do a little bit more complicated investigation where you need to run several local tests in order to test one global null hypothesis, simply correct your significance level inside this local test using the Bonferroni correction. So that's a very simple and elegant solution which you can use. Okay. I also have an app about the Bonferroni correction where I simply simulate this case, and then you can see indeed how the Bonferroni correction works. Next short video will be about how to use this app, what it shows you, what it consists of, and then I highly recommend you again to go to Grasp and play with this app a little bit, because I believe you will get better feeling, better understanding of how Bonferroni correction works, and then come back. I'll provide you a better solution, what to do if you have several populations, more than 2 populations.